Hello, everyone. My name is Pat Kinney. I'm the Beverly Brown Professor of Environmental Health at the Boston University School of Public Health and a member of the CAFE Coordinating Center team. I'm delighted to welcome you to the December edition of the CAFE University webinar series. These monthly webinars are intended to be educational and to cover various climate and health topics presented by both CAFE internal team members and by visiting experts and lecturers from across the world. Content varies from live data science-related tutorials, grant writing tools and tips, and lectures on advanced topics within climate and health. All webinars are made freely available on the CAFE YouTube site afterwards. Today, we are extremely fortunate to be joined by Professor Antonio Gasparrini from the Department of Health, Environments and Society at the London School of Hygiene and Tropical Medicine. Professor Gasparrini has emerged over the past decade and more as a global leader on the study of climate impacts on health. As a biostatistician, he developed and made freely available the distributed lag nonlinear modeling software, which has become the central tool for time series analyses of climate and health data. He also leads the multi-country, multi-city collaborative research network, which develops and analyzes a data set of health and environmental data for over 900 cities worldwide. I counted at least 2 dozen publications from that consortium just in 2024 alone. The title of Professor Gasparini's talk today is An Introduction to the Case Time Series Design for Climate and Health Studies. Professor Gasparrini, I'll hand it over to you.
Thank you very much, Pat. Thanks to you and, of course, the other organizers for this workshop. I'm really, really glad to be here. So I will start by quickly introducing what I will be talking about and a bit of a schedule about the different types of things we are going through in the next 1 hour and a half. So this is not new anymore, study design that I developed and presented a few years ago with a first publication, I think in Epidemiology, I think it was 2020. It has been used a bit, but not massively yet. So I think it's still rather new in a way, something that will be interesting to discuss with all of you. So there will be a first presentation on the method, on the methodology and the case time series design, quite broad, and in particular, linking it to previous similar designs from which, let's say, it originates, and I would say probably it generalizes. Then later, there will be 2 case studies introduced by a brief introduction and presentation first, and then we will go through proper analysis, showcasing in a way these specific case studies using R and RStudio in particular. So what I'm doing now, I'm trying to share my screen. Let me see which one it is. So I hope you can see my screen. I will make the presentation full screen, and if everything is fine, I will just stop my video so you can focus on the presentation. I assume everything is fine, but let me know if not, and I will start from here. So this new methodology called case time series, what is the motivation and the context? If compared to just a few years ago, there is a lot of developments in data science and data technologies across the world for many different applications. And also, of course, for epidemiological research, which has provided huge changes in the field of epidemiology, in particular about the type of data you can access and the format of this data and the nature of this data. And in particular, we can focus on a few specific developments, for example, data linkage of electronic records, real-time technologies to measure, in our cases, working in environmental epidemiology, on environmental stressors, for example, pollution, temperature, and many other, let's say, stressors from the environment. And these can be collected now in real time through technologies just like mobiles or remote sensing. What happens is that out of the blue, we are able to collect large population-based data sets in which you have longitudinal information with a lot of measurements of individual level risk factors, and in particular environmental factors, but also detailed information on personal characteristics. So the field, let's say, has moved from the analysis of large administrative databases, mostly at aggregated level, and exposure linked at aggregated level, to be able to measure everything at the individual level for huge populations with a detailed type of information for a long period of time. So, of course, this provides a lot of opportunities, but also methodological and practical problems. One of these problems is that you need to analyze complex individual risk profiles that, as I said, they are being collected through these longitudinal repeated measures of time-varying health outcomes and predictors. And what happens here is that, of course, there are already epidemiological methods to deal with this kind of data, but these epidemiological methods can be a bit limited if compared to the new setting. And you would like to have something more specific. The other problem is practical and more specifically computational. That is, you have such large data sets that running and fitting the usual, let's say, regression models that we are using for standard and traditional analysis in epidemiology and environmental epidemiology are probably not good enough and ill-suited for this specific setting and big data setting. So in order to deal with that, the idea is to develop new methodologies that can be at the same time flexible to analyze these complex individual and longitudinal patterns, but also efficient in terms of analyzing these data in a computationally feasible way. So in order to introduce the setting, I will present a methodological case study that you can see. It will be a very simple case study illustration about the kind of data we can deal with. So in this case, I'm showing something that is very general, which is some people, in particular in this case, 4 subjects. Of course, you should multiply this number for probably millions in some cases, that are followed in time. And in particular, they are followed for specific periods that can be different from each other. At some point during this period, this subject can experience exposures, which are these banded areas here, and or they can experience some events, in this case, any kind of health outcome that we want to study, basically. So, of course, this is a very simple situation in which subject 1 is followed from this period to this period. It has, in this case, 2 exposure periods, in this case, but of course, exposure can be also continuous, and they experience one specific event at this time, and of course, they can experience more than one event during the follow-up period. The same is for subject 2. Subject 3 is followed up, but doesn't have any event during this period, and subject 4 is followed for a briefer period of time, but still they have an event and within an exposed period. Now, this methodological case study, this general example, can refer to many different situations in which we want to measure short-term or transient associations. And I will come back to this later, which is, for example, you want to look at physical exercise of myocardial infarction, which is a clinical study. So this will be myocardial infarction. This will be period of physical exercise. Another situation can be air pollution and asthma exacerbations, which is environmental research, what we are focusing now. And the other can be instead something completely different. For example, in pharmacovigilance, you can have a paracetamol use and gastrointestinal bleeding. So this is a, let's say, general example. The idea is that how we analyze the data, for example, if we focus on our setting, air pollution and asthma exacerbation, can we use this data to assess if there is an association and how strong it is between being exposed to air pollution and having an asthma exacerbation? Now, traditional epidemiological studies usually in the past, let's say, they usually to rely on cross-sectional or longitudinal comparisons across subjects. So, for example, if you want to run an analysis using a Cox model, in here I'm running a typical survival analysis, what happens actually is that for each case, which is this, in this case can be an asthma exacerbation, you define a risk set which comprises all the people actually in the study at that specific period, depending on the time axis of the Cox model. And these are the people who didn't experience the event at that time. They are controls within this risk set. So you define a series of risk sets for all the events, and basically this is how you derive the likelihood for your Cox model, and you fit the model and you define some estimates. Now, why this is not ideal in our setting is that you need to account in this setting for potential long list of time-varying and time-variant predictors. Thinking about this context about air pollution asthma, you should explain how different people are exposed and having a different baseline risks of having asthma at each time, and also account for potential variation in this risk in time related to many other predictors. There can be time trends and everything. Of course, you are exposed to bias due to unmeasured time-variant confounders. Subjects are different in many different ways, can have completely different baselines for asthma. And of course, it's very difficult to measure and directly include in the model all these types of problems. Also, the situation here is computationally demanding because you need to measure time-varying predictors for the whole cohort, and also to run this analysis on the whole cohort, which can be composed of millions of people in this case, and therefore you run out of memory quite quickly, even if you have very powerful computer. So, given the setting, there was the idea, some time ago, I would say a few decades ago already, to take a different approach, and instead then looking at what we call a between subject comparison, which is what is at the underpinning, in a way, the Cox model and survival analysis, to look at a within subject comparison. So the idea is that in here, instead then looking at a specific risk set and looking at who is having the event in that specific risk set, you define a risk set which is within subject. So it's different times for the same subject. So the question is different. It's not who's having the event, but when this specific person has the event. So you compare, in this scale, between subjects instead than within subjects. Now, why this approach is extremely well suited in this and other context? Because it has essentially two main advantages. The first one, which is probably the most important advantage, is that in this way you control by design for time-invariant risk factors. And you do so because everything that doesn't vary in time doesn't vary between controls and cases in the same risk set, because it's essentially the same individual, and anything related to diet or related to genetics and anything that doesn't change quickly, at least in time, doesn't confound by definition. So you reduce the set of potential confounders if compared to studies requiring separate controls, or let's say a between subject comparison. The other, probably still important, but probably at least less known advantage is computational efficiency, meaning you run the analysis, first of all, only on people having an event, and you exclude completely from the analysis all the people, and there can be many, who didn't have the event during the study period. And therefore, you reduce a lot your sample size. The second part, and probably we'll come back to this later, is due to the specific form of the estimators we are using in this kind of modeling that are specifically well suited and efficient in this setting. Now, a note, all of this is only applicable for the analysis of what I called at the beginning, transient or short-term effects associated with intermittent or generally time-varying exposures. Coming back to the setting of environmental epidemiology, basically we look at short-term effects of environmental factors, just like temperature, pollution, or many other time-varying stressors, and we limit our analysis on the short term of their potentially multiple effects. So if you think about air pollution, we are looking just at day-to-day variability in air pollution and day-to-day variability in risk related to that, not to chronic effects that, in a way, can happen in a longer time frame. Apart from this, there are already existing studies that rely on this, what we call within-subject comparison, and these studies are categorized as the so-called self-matched methods. Now, there are many of them, but the two most important ones are actually the case crossover and, probably less known in this context, the self-control case series. Now, we'll introduce all of them separately, focusing more on the case crossover for obvious reasons, because it's more known probably to environmental epidemiologists. Now, this was actually originally developed in clinical epidemiology. Malcolm McClure at the beginning of the 90s, I think the paper in epidemiology in 1991, if I'm not wrong. And however, since then it has been extended in other areas, but quite a lot in environmental epidemiology. As we'll see later, is based on a so-called case control logic. The idea is to select a controls period for each outcome event. The second one is a study less known, as I said, which is the self-control case series. It was originally developed in vaccine epidemiology, rarely, honestly, applying beyond the clinical setting. Was developed by a mathematician, actually, at the Open University, Paddy Farrington. I think the first paper is about 1994 or 1996, and it's probably completely the opposite of the case crossover because it's based on a cohort logic. Well, individuals are followed up, outcomes events are identified in exposed versus non-exposed periods. And I will come back to this difference later. Now, let's start with the case crossover. Basically, the idea, coming back to exactly the same setting I described earlier, which is a specific subject, let's say, specific set of subjects followed in time with exactly the same data. The idea, instead than sampling this way, which is between subject, we look at within subject comparisons, and basically for each specific event, we assign one or more control times, let's say. So as I said earlier, the question is not who is having the event between the subject at a given time, is when the event occurred in a specific selection of cases and control times within the same reset of the same subject. Now, the statistical model, don't worry too much about the algebra. It's only helpful to explain a few things later. The idea is to model what we call the hazard for subject I, which is modeled as a kind of baseline measured through this, plus some terms which are associated, let's say, with measurable factors. In this case, think about pollution or any environmental factors. Everything is fitted through a conditional logistic regression as a product of risk sets. We'll come back again later on this idea of defining the likelihood of this model as a product of risk set terms. And basically, the idea is that the likelihood is very simple to develop and very and very efficient. Now, the good thing of this model, as I discussed it earlier, is that these kind of terms here, that the model, the individual level, let's say, successibility or baseline risk, basically, it can include, it can be modified by many different things, meaning, as I said before, diet, genetics, etc. The good thing is that, as you can see from the likelihood here with this derived, these terms here are, we say, conditioning out from the model. And what happens in practical terms that anything related to the baseline characteristics of the individuals, meaning anything non-time varying, is actually not affecting the likelihood anymore at all. That is, they are controlled simply by design. The other issue, the other advantage is that, as I said before, the estimation only involves resets defined by the subject experiencing the events, and therefore anybody not experiencing the events is not included in the analysis at all. And therefore, for these two reasons, that you define the analysis only on the cases, and the likelihood is defined as a sum of subject-specific terms or contributions, everything is computationally very efficient. Now, before going forward, I'll start addressing some, and let's say, busting some myths about the case crossover analysis. The first one is that the case crossover, as it is defined in here, involves a density sampling, and therefore the interpretation of the exposed coefficient from a logistic regression is actually a risk ratio, and not, as many times reported in the literature, an odds ratio. Meaning, if you fit a logistic regression in a case crossover analysis, although it's a logistic regression, what you get is an estimate of a risk ratio, not an odds ratio. We can discuss later if you are interested. Now, the interesting thing of the case control design is that in time, there's been many different sampling schemes for selecting the controls. In the original study by McClure, these controls were sampled unidirectionally, meaning somebody's having a myocardial infarction here in the original study, you sample some controls in the past, basically, especially for the reason that some subjects are not followed up later because they had the event, and in some cases the event can also be death, and therefore these subjects, they don't exist anymore after this time. Now, in time, other types of selection or sampling scheme has been developed, especially because this specific control schemes is potentially biased by the presence of trends in the exposure. So if the exposure is decreasing or increasing in time on average across the subject, of course, this comparison will be biased. So in time, other types of sampling has been proposed. In particular, one of them is this bidirectional sampling, in which instead of sampling only on the past, you sample both in the past and in the future. Now, this implies already some assumptions. One of the notable assumptions, which is probably also rarely mentioned nowadays, is the so-called rare outcome assumptions, meaning because in most cases the subject is not followed up anymore in the future, you need to assume, in order to allow a sampling from the future, you need to assume that this outcome is rare. If it's not rare, you will have a bias in the estimation. The other thing that you need to assume is that the exposure, and we'll see more on this later, is exogenous, meaning is not affected by the fact that the subject had the event. And therefore, this is actually happening quite a lot in environmental epidemiology, because, of course, levels of air pollution that somebody could potentially be exposed to are not influenced by the fact that these subjects had or not a specific health event. Now, less known is that both of these specific schemes I described are affected by bias. In particular, these overlap bias. There are very interesting references and publications, especially by some groups of colleagues in the United States, I think Thomas Lumley and others, describing these types of bias. And basically everything is because there's a lack of exchangeability between cases and controls. The main idea is that the event could have happened in any of this time, but because the controls are sampled either only earlier or one earlier and one later, they have a predetermined positions within the reset that create this kind of bias. Now, also these things have been solved already some time ago, basically coming out with another type of sampling, which is the so-called time stratified sampling. In this sampling, instead than sampling either only before or before and after, you predefine the reset in terms of a specific period. Most of the time you will see is a month, and independently by when a specific event happened, you sample both before and after within these predefined windows. The most common ways is to define, for example, the same weekday in which of the months in which the event happened. So, for example, let's assume that there is an event in a specific month on a Wednesday. You sample all the other Wednesdays as controls. This time stratified scheme is unaffected by overlap bias and therefore is the most commonly used nowadays. Now, as I said, this was the case crossover design. The alternative design, that is, and as I said before, this case crossover has a case control logic. Basically, you have a case and you sample controls. An alternative design was this self-control case series. Basically, you have exactly the same situation, but you follow up continuously subjects for a specific period. You define within this period exposed versus unexposed period. And basically, you measure in each subject the rate of having specific events in exposed versus non-exposed periods. So, differently from the previous situation in which you compare if a subject was more likely to be exposed or not if compared to controls, and therefore you have a case control scheme or logic. In this case, you have a cohort logic. Therefore, you compare exposed and non-exposed periods, and you look at the rate of the events in exposed versus non-exposed periods. So it's more or less the same idea, but in here you use a cohort logic and not case control logic. Now, this self-control case series, as I say, it's not very known among environmental epidemiologists in particular, because it was developed especially in clinical studies and in vaccine epidemiology in particular. But I would probably recommend some of you to have a look at the literature on this, because the framework is developed in a very elegant way with a set of well-defined assumptions that helps a lot the discussion that we'll have later. Now, all these studies, the case crossover and the self-control case series and many other self-match studies, they have some limitations. First of all, they are only applicable for event type outcomes, but for example, they are not applicable, as an example, to continuous outcomes. For example, if you measure cholesterol level, you cannot apply a case crossover analysis. Some of them are not applicable with continuous exposures, for example, the self-control case series, or it's hardly applicable with rare exposures, which is the case crossover, especially because most of the reset, just because you sample specific times, would probably be non-exposed or for both cases and controls. It's difficult to control for time-varying confounders, difficult to model temporal dependencies, and there are some complexity, especially for the case crossover, with selecting the sampling scheme. In general, however, we can say that in both cases, you, in a way, forget in all of these that these data longitudinally structured, meaning you don't take into account the longitudinal nature of the data. Now, there is another study design that does that explicitly, which is the time series design. This was developed, probably many of you already know, in econometrics. Well, I say only recently applying in environmental epidemiology probably is not true. It's been applied in environmental epidemiology probably from the early 90s. Joel Schwartz, some colleagues, a colleague of yours in Harvard, was one of the pioneers of this method, and it is rarely presented as self-matched study, but in fact it is, and it has some requirements. For example, observations collected at equally spaced and ordered time points. Now, I'm mentioning this because this was probably more of a problem in the past. Nowadays, as I said at the very beginning, equally spaced and ordered measurements for both exposures and outcomes, health outcomes, are very much available because of this revolution in data science. Now, there can be several examples of applications. The advantages of this method: you use it mainly with routinely collected data, so it can be run very quickly and cheaply using administrative data you have already. One of the main limitations, however, is that it is mainly based on aggregated measures, meaning is a study applied to aggregated data, and therefore you are, of course, more easily exposed to ecological biases. Now, what is the idea of this? Is that you can think about the original design that I presented at the beginning. Basically, what happens is that that is a single population in which you had a longitudinal setting with this daily, most of the cases, observations, and in some observations you can have one, or most of the cases many more counts of events, and you are looking basically within the series of the likelihood of having more events in exposed period or more exposed periods if compared to less exposed periods, many periods, let's say days in which the exposure was lower. Now, again, it's a very flexible design framework for which advanced analytical techniques have been developed, and there are nowadays established, let's say, regression models to run it. I will introduce them here. Basically, you're looking at an outcome which is in most cases counts of events, and you model it as a series of terms, the most important of which is a function f, which models the association with the exposure of interest, x. And of course, you have other terms. One in particular, very important, is one or more functions of time to control for trends and seasonality, and also another one controlling for other time-varying confounders. Now, this is usually run with a generalized linear models. The only peculiarity is that everything is indexed by time, of course, and not a subject. Now, as I say, the time series has many advantages, especially because there are flexible modeling techniques. Some of them, for example, smoothing methods to control for trends, or distributed lag linear and nonlinear models to define complex b-dimensional exposure lag responses, in which you can have both non-linearity in the effects, but also lagged effects. Now, we don't have time to spend here for going through all of these, but of course, all of this is established now in the literature. So eventually, the idea here, you have extremely interesting self-matched individual level type of designs, for example, the case crossover and the self-control case series, and at the same time, you have very flexible designs that accounts very neatly and exploit very neatly the temporal structure of the data, which is the time series model. And the idea is that to put them together in the so-called case time series design, What is that? Is a design in which you still keep the analysis at the individual level, but you subset, in practical terms, the follow-up of the individuals in individual specific series. So you keep the individual level of the analysis, but at the same time, you put a time series structure in it. And this allows the reconstruction of longitudinal profiles instead of time series of health outcomes and time variant predictors at subject level, individual level. So at the same time, you can exploit the individual level setting of the self-matched designs and the flexible modeling framework of the time series. Now, the modeling framework, not unexpectedly, resembles very much the one of the time series. So you have exactly the same terms in the times of the time series model I described earlier. However, you have two specific issues. First of all, everything is indexed not just by T, but also by I. Therefore, you have multiple subject-specific series. But more importantly, you let's say you retain this term specific that we have seen in the case crossover, which is a subject-specific intercept, which can model differential baseline risks across subjects. And actually, in this case, you also can subset these by specific time periods within the follow-up of the subject. And therefore, you can assign different baselines, not just to different subjects, but to different periods within the same subject. And as we can see, and we'll see later, and already introduced in the case crossover, these terms here can be conditioned out from the likelihood, and therefore you can control quite aggressively for both time invariant characteristics, as I said before, diet, genetics, etc., by design, because you don't have to measure, but also you can control for individual level time trends, because you subset, similarly to the case crossover, the follow-up of the individual in multiple strata terms. Now, through this, you can exploit also the usual techniques developed for time series analysis, for example, distributed live nonlinear and nonlinear models, smoothings and methods, and all the rest. However, as I said before, if the modeling framework resembles the time series one, the estimation and computational aspect, as I already mentioned it, is very much similar to the self-matched methods, in which you run conditional models in which these terms, specific subject-specific intercepts, are treated as a so-called nuisance parameters and conditioned out. This has been done in the past in panel data analysis, and eventually you end up using the same methodologies, which are these fixed effect or conditional models that, however, exists not just for the Poisson model or for example, for some analysis, or for the binomial, for example, the conditional logistic regression, but for also others, distributions, in particular, also for continuous outcomes as a fixed effect linear model. Now, this means that you can use this approach, which is this case time series, for any kind of exposure and outcome you can have. So you can use it in a typical situation in which you have a count outcome and a binary indicator of exposure. You can have a binary outcome, meaning just 0, 1, and continuous exposure, or you can have a continuous exposure and continuous outcomes. And in all these cases, you just run a conditional model for that specific distribution. That can be a Poisson, binomial, or Gaussian for in all these cases. And therefore, the applications of this methodology are much broader. Now, some caveats, however, that similarly to the other previous models that I discussed designed that I discussed previously, in particular the case crossover and the self-control case series, there are very specific and strong assumptions that you are making when using this data. Now, these assumptions, they apply to any self-matched studies. So it includes the case crossover analysis, the case time series, and all the others. The first one is distributional assumptions of the outcome. This is probably a given. They are conditionally independent distributions originating from one of the standard family, as I said before, Poisson, Bernoulli binomial, or Gaussian. Another more complicated assumption is the follow-up period should be outcome independent, meaning having an outcome doesn't interrupt the follow-up of the subject. We have mentioned this already earlier in the case crossover when I say that in order to allow a bidirectional sampling, you need to make some assumptions about the rare outcome because effectively, in some cases, the subject is not under follow-up anymore. So again, this applies to the case time series as well. You can only use it in this context and with this assumption. Another even more important assumption is that an outcome-independent exposure, meaning having an outcome shouldn't modify the probability of being exposed in the future. Again, we rely on these applications for exogenous exposures, for example, environmental exposures, in which me having an outcome, for example, myocardial infarction or asthma attack, doesn't modify air pollution levels, or at least air pollution levels outdoor, let's say. Now, another one, probably even more important, is this constant baseline risk conditional measured time varying predictors. What does it mean? That within the risk set that you define, there can be the follow-up period of an individual, or in these applications, most of the times, a specific stratum of these, apart from changes in risk associated with this specifically covariates that you can directly measure, the risk, the baseline risk, must be constant, meaning there are no trends within the risk set that are not directly modeled, basically. Now, if you're happy with this assumption, of course, you end up with very flexible and adaptable framework, which first of all combine the flexibility of the time series and the design features of individual level K self-matched methods, let's call them this way, is a general one, so it can be applied intermittent or continuous exposures, event type of continuous outcomes that is much broader, for example, than the case crossover, is flexible because it keeps the longitudinal structures provided by the time series type of data, and therefore you can model, for example, distributed lag models or apply smoothing techniques. And as I say, it has a wide applicability for investigating a broad range of health associations in different areas. Now, I put here some of the main references so far for some of the, for example, applications of this method, but in particular, probably I will focus on these two links in here, which are specific tutorials or examples with R code that you can follow. And what I'm doing now, we start with some of these examples. The first one, I will start it by introducing it very quickly, and is an application in a smartphone study. Now, why we are interested in this setting is that because smartphone technologies, they provide incredible opportunities for epidemiological research, especially in environmental epidemiology. Why? Especially because they can collect in real time continuous observations at individual level, which is something that is less obvious, let's say, in environmental epidemiology if compared, for example, to clinical studies, etc. More importantly, the smartphone can follow you through geolocation, and therefore you can trace individuals in time and space and follow them up and also link these locations, for example, with maps of high-resolution exposures, and therefore assigning exposures at the individual level, not just outcomes and risk factors, but also accounting for the movement of individuals around. So this context offers optimal data setting for the application of the case time series design. In this specific study, we look at a specific hypothesis that multiple environmental stressors exacerbate the risk of allergic symptoms. We use data for a study in Tasmania in which people, 1,600 people, were followed during a 3-year period, and they reply with daily questionnaires to a smartphone app called iRater, I will introduce in a moment, and also their environmental measurements were followed and assigned with environmental measurements of exposures. Now, the analysis, it is a nice application because it allows you to look at complex temporal relationship between continuous exposures and repeated measurements of outcomes. And the objective is to how you can use the case time series in this setting. So this was the app. The app was downloaded by participants, and these participants were daily providing information about reported allergic symptoms and potentially related aspects, for example, sleep, mood, activity, etc. And they were followed up and assigned exposures. Now, this is a profile for a single subject in which you can see during a 3-year period when this subject reported some allergic symptoms in a day as a 0-1 exposures. And for all this period, we have the continuous monitoring of the subject for pollen, PM2.5, and temperature. And this is at the individual level. So the analysis, we'll see later, is very simple to run. This will be a conditional binomial GLM. Binomial because it's not a count. It's an indicator of having a specific allergic reaction. And the exposure are the 3 exposures we mentioned. The idea is that you stratify not just by subject, but also you define risk set by periods, in particular defining monthly stratification for that subject. And also you add a control for temporal control in addition to this, with natural cubic splines, etc. Now, I'm not discussing the model very much, but these are the kind of results you can get of this model that we'll discuss in just a moment. And it shows in a way how you can successfully apply this case time series analysis in a relatively complex data setting in which people, you can imagine, are just dropping in and out continuously from the study because they were using the app for 1 month and then stopping, etc. From the setting point of view of a epidemiological study was a very complex one, and it shows some advantages of this case time series. Now, quickly, we can see how you can do this in R using some data that I completely, let's say, simulated for these cases. So we are loading some standard packages, in particular GNM, which is this package for running generalized nonlinear models that we will use for running these conditional models for fitting a case time series analysis. Now, the first data that we load is this data set that just showing the first part of it, which for each subject includes the start and the ending period, basically the follow-up of this subject. Second, we look at the symptom data. So the symptom data has one or multiple events in which the subject reported in a specific day a specific symptom. And finally, we load the M data. The M data is environmental data with which for each date you have measures of pollen, PM, or temperature. Now, this M data, for practical purposes for this example, is just a single series, but you can imagine that this can be assigned at the individual level, and it was in the original application and study. For practical purpose, we are using a single series because it's easier to load and to assign to the subject. So the first thing you do, you create this so-called case time series structure of the data. Now, this is done basically, first of all, defining the series for each subject and stacking all the series together. Now, this can be done, unfortunately, I haven't written in here, but more efficiently with data table. You can find some code maybe in the examples online if you want, but basically what you get eventually is this type of data in which you have for each ID subject, the complete series stacked together between subjects. Then you define some time variables. Then you define symptoms days in which for each of the symptom of the dataset symptoms, you assign an indicator equal to 1. You merge it with the original data and you fill with zeros when needed. So you end up having a situation like this in which subjects, they don't report symptoms for most of the days, but in some days they do. And finally, you merge the environmental data together. Of course, in this case, it was very simple because you have a single series. Imagine that naturally you will have to do this at the individual level. So you need to assign individual level measurements of exposure. And this is your so-called final case time series data set in which you have a series for each individual, in which you have time variables, a measure of outcome, which in this case is just an indicator of having an allergic symptoms, and a series of exposures assigned at the individual level. So you do some descriptive analysis. I'm not going through the code. Feel free to go back to that later. Of course, you will have access to it. This is the kind of data I presented before, in which for this specific subject, which is this subject here, you have the outcome series, which is when they reported an outcome, and the specific exposures for all the 3 different environmental stressors. Now, final part, which is probably the most important, which is running a regression model and a so-called case time series analysis. First of all, you define some degrees of freedom from the trend, which are 24 in total, because there are 8 per year. As we'll see later, probably this part is not very important because you also apply an individual level control for trends. By you defining here a spline of date to control for these common trends. And then more importantly, you define a so-called stratum, which is, in this case, a subset of the data corresponding to a specific month within the follow-up of a specific subject. So this subject is followed for August, then is followed for September, and you assign a different stratum to each of these. Now, of course, this starts becoming a bit technical. Probably some of you knows the methodology as well. We apply distributed lag linear or nonlinear models to model the effects of each of the 3 exposures, pollen, PM, 2.5, and mean temperature. And you define these terms for these distributed lag linear nonlinear models with this function cross basis in the DLNM package. So you define the 3 cross bases for the 3 different environmental exposures. And then we'll go through the parameterization of them later. And then you just run the model, which is a model that resembles very much a generalized linear model, but is run with this generalized non-linear model, in which you have 2 important differences. One of them is this eliminate argument, which basically defines the stratum, basically defines the risk set, which in this case, I mentioned it earlier, it's the month within the follow-up period of a subject. The second issue is that you run it with a binomial family, because this Y here is not a count, but just a 0-1 indicator. And therefore, effectively, you are not running a Poisson model, but you are running a binomial model through which you derive basically a measure of odds ratio and not risk ratio. Now, you run this model, it takes a bit probably to run. While it's running, I'll explain the next part, which is extracting predictions from these distributed lag nonlinear models to represent in a way the effects for the three different predictors, and you do it with this function cross-spread that some of you already might know, and therefore you define the different effects and then you can plot them. So this is the effect of pollen, showing that you have as a cumulative part increasing risk that tends to level out, therefore on some nonlinearity. So for very high pollen level, let's try to zoom a bit on it. For very high pollen level, you have a risk that starts to attenuate, and this is the full exposure lag response relationship, showing that there is also some evidence of a lagged effect up to lag 2, let's say. Now, different is for, sorry, this is not pollen, is PM, actually. So in this case, we assumed a linear effect, so we fitted a distributed lag model. So you force the effect to be linear, and you look at an unconstrained distributed lag, therefore treating each lags separately, showing that the effect seems to be confined to lag 0, meaning PM seems to have an effect on allergic reaction only on the same day of the exposure, basically. Finally is temperature, again, not pollen here, apologies, I will correct it later. And in here you can see that as in many other situations, you have a non-linear effect of temperature that with a flat effect up to, let's say, 15 or 17 Celsius degrees, and then the effect starts increasing, and again there's some evidence of a lagged effect of temperature as well. Now, in all of this, you can see how you can apply typical time series techniques, for example, for smoothing or for distributed lags, however, in analysis run at individual level. Now, we stop here with this example. Of course, we can discuss it later, and we come back to a slide to introduce the second example, which is a case time series with aggregated small area analysis, and in particular to look at an investigation of heat-related mortality risks. Now, small area studies, again, are becoming more common, especially because through data linkage and environmental monitoring, you have available health and exposure data at higher resolution more commonly than just a few years ago. So you can assign local exposure values to area level difference and investigate also area level difference of vulnerability. This allows performing small area studies on disaggregated data. So it's still aggregated data, but they are not a single series, but you can think about having multiple series for specific small areas within the location of the study. The case time series analysis was originally proposed for individual level analysis, but can be easily adapted in this context. Basically, the unit is not a subject, but it is a small area. Now, as an application, we look at this case study of heat and mortality risks. So using high resolution health exposure data, I decided to show this example because in which you can use publicly available real data, which has deaths in London during the summers, 2 separate summers of 2006 and 2013, between June and August, in 983 middle layer super output areas, which are basically census-based areas, which are relatively small, and there are 983 in London. So the analysis, the idea is capture risk of local exposures, basically local temperature measurements, and assessing vulnerability differences across areas And you can do this using the case time series. So, first of all, the idea is that in this case, you disaggregate what you have usually, which is a single time series, for example, of deaths for the whole London. You disaggregate in time series at each unit, which in this case is a single MSOA or small area. And you can see in most of the MSOAs, in most of the days, you have no deaths. Sometimes you have one death, very rarely you have two. But of course, it's very rare a death in this small area. So therefore, you analyze all this data together in a single model. The other good thing is that you can have high resolution exposure data. In particular, in here, I'm using this 1 kilometer grid database that in which you can see here the single cells of 1 kilometer. Of course, London is a big city, approximately probably, I don't remember, 60 kilometers wide, Greater London or something like that. Of course, you have bigger cities in the United States. And for each of them, you can have a different exposure. In here, I'm just reporting the season average for 2006 and 2013. But the idea is that for each of these cells, you can have a daily values. And of course, these daily values can be assigned then at each specific small area. In particular, here, I'm reporting the 983 MSOAs in London. You can see some of them are big because are mostly residential, let's say, almost rural areas in the city center of London. Of course, these are very small because it's very densely populated. Now, the main analysis includes 23,000 deaths across the MSOAs during the 2 summers. In this case, we are applying a conditional Poisson model because we have effectively counts of deaths in each day in each MSOAs. Still with this, using the same function GNM, as we'll see. The outcome is MSOA-specific daily counts of deaths. The exposure are MSOA-specific daily mean temperature, and the stratification, again, is for not subject, actually, but it's MSOA period risk sets. And again, the periods are monthly periods within the same MSOAs. So you can see that from this model, you can run an analysis and get an estimate of the exposure response for temperature and compare it also, we'll see later, to a typical aggregated single time series analysis, but also you can look in for the case time series also at the effect modification of area-specific indicators. For example, in this case, IMD, which is an index of multiple deprivation, basically an index of poverty. And you can see if this is an effect of modifying the exposure response for temperature and mortality. Now, of course, still some comments, very useful here because you show how you can use this method in a analysis of data disaggregated by small areas, looking at local difference in exposures and risks and in a very flexible way. Now, I come back to R because there is the second script in which through which you can run this analysis. Now, this is a bit more complex because the data linkage in here is not as straightforward as for the smartphone study. So you run some more packages, in particular some packages, these ones that are related to GIS method in order to do this linkage and mapping. But let's start from the beginning. So we erase all the previous data. We load a first data set. Of course, this will be made available to you as well. This data set is the real original data set. So this is available, if you look at the publication, in the Office of National Statistics website. You can download it from there as well. And it refers to each record to specific number of deaths for 75 and older people or less than 75 in a specific MSOA in London. In particular, this one is the Barking and Dagenham 0.03 MSOA for a specific day. So these are the original data. What you do with this data, first of all, you start doing some manipulation. and therefore you create sorry, no, it wasn't this one. You create a date out of this, then you define a series of unique MSOAs and dates, which is a sort of sequence of MSOAs and sequence of dates. And then you start preparing the so-called case time series dataset. So you do it using pipes in here. The idea is that, first of all, you expand these two and you transform it in a data table object. Now, I didn't mention it, but data table in these situations can be very useful because it allows you to deal with very big data sets. In here, I expanded a series for each MSOAs. In this case, it's just by the same date across all MSOAs, but of course it can be reordered. Then later, you merge some of this data or each part, only some variables, in particular MSOA, the two age groups and date, and then you also add separately the MSOAs names, etc. So you end up with this data pool, which is the fully expanded case time series data sets in which for each MSOAs you have the complete series and indicators of an event, meaning one or more events, basically deaths happening in a specific MSOA. After that, you fill the non-event days with zeros. Then you create total mortality by summing deaths in less than 75 and 75 and older, and you define also some typical time variables, and then you order everything in a data table format with this command set key. Now, in order to do this, you can also want to compare this with the usual time series analysis. And in order to do that, what I do, I aggregate this data using a data table, in a way, syntax, and therefore you come up with this single series with deaths for 74 and 75 plus and total, which is the typical time series that you will use in any standard time series analysis. Then, of course, also for this one, you create the time variables, and then, of course, you can do some plotting, including both the aggregated and and disaggregated series, as we saw in the original presentation. So this is the total series of total deaths in London. This is the MSOA specific series disaggregated. Now, more complex now is linking the environmental data, especially because I have these rasters of data on a grid, 1 kilometer grid at daily level. So I load first the shape files for London, including basically the this is a kind of SF file, including the polygons that defines the MSOAs. I load the grid data, which is in a netcdf file that will also provide it. Also, these one are netcdf files that can be shown this way. Of course, both of them probably we can plot them. So you can see these are all the MSOAs in London, and this is a, I'm not sure, let me see if it works. It should, yeah. So this is the temperature series for the first day in the series in here. So you have the two information that you want. So you can first of all run a relatively complex code that I don't have time to go through, but basically showing these two information overlaid one on top of the other. So as shown earlier in the presentation, you can have the original raster and overlaid that you have the polygons. So the idea is to assign measures to these polygons based on the raster. This is a typical GIS method. We use this function exact extract to do this matching, and eventually you run it and you attach it to the data full. So now in data full, you have also the level of T mean, which is the area averaged T mean from the original raster for this specific day, but also you can then aggregate it also to the let's say aggregated type of data, which is this one. Oh, sorry, I haven't probably done it yet. So this one, in which you have also, oh, sorry, I think I did it twice. So sorry about that, but I need to rerun everything from the beginning. So now you have T mean also aggregated that, and this is actually the aggregating together, averaging together all the MSOA levels across London. Now, probably I will take just 1 minute to explain this. You can take some measures about what is the variability between days and between MSOAs, because this is important to analyze the results. Basically, the between day variability tells you how much is the variability between days within the same MSOAs. And this is the standard deviation, saying that is a 3.101 Celsius degrees of variability. Instead, this is the between MSOA variability, meaning in the same day, what is the variability in temperature across MSOAs, and you can see that it is much smaller, meaning there is more temporal variability than spatial variability. However, apart from this, now you have your full data, so you have your linked data in which for each day you have a differential exposure in each of the MSOAs. And from here, you can finally run your model in which you define a spline for day of the year, which is to model this common seasonal trend. Again, you define a cross basis of T mean to model the exposure lag response relationship between temperature and mortality. You define again a stratum, and if you go in data full, you can find that this stratum corresponds to a specific MSOA in a specific year for a specific month. Finally, you just run the model. Importantly, and probably we can come back to this later, you need to exclude the so-called empty strata, meaning month within MSOA in which you didn't have any event, in particular deaths, because this is a problem of the GNM function, that you need to do this exclusion manually. Otherwise, you will have some problems of biases, especially for the confidence intervals, when you're using a quasi-Poisson distribution. We can come back to that later. However, you can run the same model on the aggregated data. This model just run a GLM model because it's a standard time series. And then you can predict and plot. And this shows the exposure lag response between temperature and mortality in summer with the case time series, and we aggregated data analysis. Now you can see that the effect of heat is captured by both of them, but you can see that the case time series look at a wider range of exposures, especially because it models disaggregated data, and therefore the aggregation results in the other model in a shrink in a way of the of the exposure distribution. So similar results, but probably the case time series can identify more patterns, particularly this suggestion, at least, of a residual cold effect in the summer, which is not captured by the usual analysis. In addition to this, I'm not going through the code, but basically, which is relatively complex, but you can look at the interaction effect, because just because you have individual level data, basically now you can takes a bit to run. Also look at differential effects by specific characteristics of the MSOAs. In this case, looking, for example, if there is a differential effect between low and high IMD scores. Remember, IMD is the index of multiple deprivation. In this case, of course, we have very low power to disentangle all this because it's just 2 seasons in London and not any more than that. So there is no power. And in particular, if you look at the results of the test reported here, there is very little evidence of an effect. But of course, you can replicate this analysis with many other indicators and potentially with a bigger data set. Now, well, I think I can probably stop here. I'll come back with you just in case you have any question. I'm really sorry. I planned it probably to be shorter, but we still have 12 or 15 minutes for questions.
That was fantastic. Thank you so much, Antonio. I'm so sorry that the first 30 minutes of this overlapped with my class. So sorry that I couldn't be here for the first 30 minutes. But I eagerly rushed back for the rest of it. And it was really an incredible presentation, as indicated by all the chatter in the chat. There's a ton of interest from folks in this topic. So thank you so much. Also appreciated your use of data table. I'm also a data table user. And yeah, you're really appreciate your making the code and stuff available so that people can also follow along and access that afterwards. So yeah, we have a couple minutes for questions. There have been a lot of questions coming in the chat. Elaine, maybe what would make sense is if I ask a question or two first, and in the meantime, if you'd be able to maybe unmute a couple of the people that had some of the longer questions in the chat, and they could just ask them themselves instead of me reading them off. And so in the meantime, I'll ask a question or two, and Elaine, if you wouldn't mind doing that, then folks could unmute themselves and ask their own questions. So one question that I had, and apologies if I missed this before I got here, but for the case time series design, suppose we have a rare outcome where a lot of individuals, even with a long time series, might have no occurrences of the outcome or only one occurrence of the outcome over their entire time series. So in that case, would using the sort of individual level formatting of the case time series like cause some instability? I guess there would be possibly identification issues with those individual level intercept parameters. So in that case, would you recommend sort of doing some aggregation up if you have a very rare outcome, and then apply the case time series on the more aggregated data?
Well, in that case, basically, the actual information you are interested in is only for those subjects having that event around the period of the event. So eventually, in that case, probably there's not much difference between the running a pure case crossover or a case time series. Actually, you can see the case crossover as being a specific application of the time series in which instead of selecting, for example, an entire month for the subject and considering it a series, you just sample the same weekdays for that specific subject. Eventually, there's not much different. Actually, it's mostly data management in which you need to put this together. But as I said in this last example, any stratum, which can be an entire subject, never having an event, or, for example, as this application, a month period, that subject not having an event, that actually doesn't contribute at all, and you can
Got it.
exclude it. So eventually,
Got it.
even if
Okay.
you have a big data set, eventually you can end up with a very small final data set you want to fit your regression on.
Got it. Okay. So it sort of reverts back to the case crossover in that
In
setting
that
with a
specific
range outcome.
situation, yes.
Yeah, got it. Got it. Makes sense. Thanks. Another quick question that I had, and then I'll hand it over to others. So you mentioned the assumption that having an outcome doesn't modify future exposures. And when I was starting to think about that assumption, it kind of made sense to me because I was thinking about a case where you're probably using some aggregate exposure, some aggregate outdoor exposure measure, and it wouldn't make sense that one individual's outcome would affect like the level of outdoor air pollution or something like that. But then when you started talking about the smartphone example, where you have this more individual level exposure data, I started thinking that like the more you get that sort of fine-grained individual level exposure information, it seems to me the more likely that this assumption would be violated, because it seems then more likely that an individual's outcome would actually modify their future individual level exposure in many cases. And so sort of, I wonder how you think about that trade-off of like, you know, you get the better, more fine-grained information, but then it might also be more likely that you violate the assumptions of the method. Am I understanding that right?
Absolutely. Yeah, it's completely correct. First of all, this applies not just to the case time series, it applies to any self-matched studies, including the case crossover. So you would have this problem anyway, even using more traditional methods, let's say. Now, it's unresolved from the case time series perspective. However, I should mention that this self-control case series, that other specific design that I mentioned using in vaccine epidemiology, Paddy Farrington and their group along the years, they have done a lot of extensions for this specific, looking at how relevant is these, there are these kind of problems, and also proposing some extensions or at least, let's say, tricks to at least reduce the types of bias you can have in this situation. So the idea is that probably this should be extended further and generalized to the whole set of designs that we are using, including the case time series.
Thanks. Yeah, makes sense. Okay, now I'm going to let a few others ask questions before we run out of time. So first, I think the folks who are able to unmute themselves, if you're able to talk, please go ahead when I call on you. So Lebo Wong, I'm not sure if I'm pronouncing it right. If you can unmute yourself and ask your question, that would be great.
Sure. Thanks, Lebohang. Yes. Thank you so much for the presentation. It was very interesting. I feel like I'll be watching it over and over for the next while. My question was much more basic. It was much more around the time stratified sampling and trying to understand why the most common application of this is to use a calendar month to create the controls, instead of just something like 2 weeks before, 2 weeks after the case occurred. Like, why would this calendar month be relevant for something like temperature exposure? But then also trying to think about like how something like heat could vary, like the variability in that exposure could vary significantly depending on what time of the year you're in. So if you're in like transition seasons versus summer or winter, and like, should we be concerned about that in the mix as well? So thank you.
Well, yes. First of all, first of all, starting from the more theoretical aspect, when I presented the case crossover, there was this bidirectional sampling in which you sample one after and one before the outcome. Actually, that sampling leads potentially to biases. It's this so-called overlap bias. Basically, the main idea underlying this is that your stratum shouldn't be defined in terms of the event. So you cannot define the stratum 2 weeks after and before the event, but actually it should be predefined. And the event, the idea to keep this extensibility between events and controls, the event could have happened in any possible time within the reset. This is the underlying practical explanation of it. This is why this method, time stratified, is used nowadays much more than the other ones. Actually, in clinical setting, they are still using quite a lot this unidirectional sampling, which sampling only in earlier times, which is actually not just biased by that, but also potentially by time trends. So it's still something not known completely. Now, apart from that, choosing 1 month if compared to 2 months, practical things. I mean, months is easier, but there's nothing special. So in some situation, you want to extend or reduce the sampling, the stratum, you can do it. And this can be done because, as you say, maybe you capture more variability in the exposure, but take into account that the more you extend the stratum, the more likely that this assumption of constant baseline is more difficult to keep, because it's more likely that observations farther apart from the other, they are different in many aspects because of trends or other reasons for that. So the selection of the window can be anything. So we use calendar months because everybody has done so, but there's nothing special about this, and probably you shouldn't stick with that if you think there's something better.
Okay, perfect. Thank you so much.
Pleasure.
Great answer. It's a hard one to explain. I always struggle with explaining that. Let's see, who's next on my list? Zin, if you want to unmute yourself and ask your question, more than welcome. Maybe they're not in a position to unmute themselves. We'll circle back. Allison, I think you were next on my list if you wanted to unmute yourself and ask your question.
Hi, I'm Allison. I'm from BU. My question was actually really similar to Rachel's. You mentioned like the case time series design assumed like a constant baseline risk after an event. And I was curious how in past analyses you've sort of accounted for like behavioral adaptation, because if someone experiences an event, obviously they're going to try to like mitigate their behavior to try to prevent it happening again. And while like new technologies such as smartphones can help reduce that to some extent, if you're looking at sort of like a national cohort or very large, that's not necessarily feasible.
Absolutely. Okay. Well, first of all, an acknowledgement. I stated the problem. I haven't solved it. So, I've never started putting myself in the position of solving. So I think this can be a very nice application for some kind of causal modeling in here, in which you should really think if this happens, meaning the having an outcome changes your probability of being exposed later. Maybe you can apply some design features or causal modeling approaches to try to not, at least to reduce this kind of biases, not to cancel it comprehensively. I cannot tell you how, because if I knew, probably I would be publishing about it at the moment. But it's an interesting area of research that maybe some of you can be interested in putting some efforts on.
Great, thank you so much.
Yeah, it's a great place to maybe merge some of this area of research with like causal marginal structural models and things like that can account for these sort of time varying factors. Yeah, this is super interesting. I think Nicholas had a follow-up question to that one, so maybe we could ask that one quickly, and then we have to hop off. Nicholas, if you want to unmute yourself and ask, you can.
Thanks, Rachel. Thanks so much, Antonio, for the excellent presentation. I'm Nicholas Blink. I'm a clinical researcher from this Planetary Health Research, so the statistics is maybe beyond me. Just extending on that, when we look at outcomes that have time varying risks, something like preterm birth comes to mind. That's something we focus on a lot. And obviously, your risk of preterm birth is going to change throughout the course of your pregnancy, where early in the pregnancy, there's a low risk. It's going to peak as you approach 37 weeks, and then it suddenly drops off because by definition, you can't have a preterm birth. it sounds like that is an issue that maybe hasn't been solved yet. One of the approaches we've discussed is potentially, instead of a way of controlling of it for it might be, rather than just assigning your controls as, if we look at sort of something like the case crossover, rather than assigning your controls as it didn't happen, you rather assign them in a sort of stochastic distribution of what was the probability of it happening in that period. And so if you have your preterm birth at 36 weeks, you know that it was, never going to happen at 37 or 38 weeks. But the week before, maybe you had a 10% risk. Is that approach that could that approach work, or do you have any suggestions on other approaches for handling an outcome like that has been used in the literature with the case crossover?
Yeah, I mean, first of all, you can define some measures of common trends and model them directly in the model, meaning you can have an underlying risk at population level that changes even abruptly from one moment to another just because you model it at the population level. So you keep the analysis at individual level, but you have a complex pattern of changing risks across the population across that. Otherwise, probably my suggestion would be probably to switch to a completely different study, which is you condition on the week. So you just compare people at that specific, having an outcome, well, having a birth, for example, in that specific week, or actually day of the pregnancy. So you are sure that everybody, they are at this exactly the same time, and the comparison between them is not affected by complex underlying patterns of changes. Of course, this has nothing to do with the case time series, or maybe you can find some links, but it's not exactly the same study. But this idea of conditioning, I think it hasn't been used enough in epidemiology, because it's a very strong way to remove biases and confounding without relying on complex modeling or complex causal frameworks, basically. So it's easier to use and to implement.
Great, thank you so much.
Thanks, everyone. This was a great discussion. I think we're a little over time already, so we should let our speaker go to be respectful of your time. But yeah, thank you so much for this fantastic presentation. For those who are still with us, this will be posted on our YouTube page, hopefully sometime in the next few days. So the recording will be there. And then Antonio, I believe, shared the links in his presentation to the GitHub for the code and things like that, right?
Well, I can do that, or I can send you the material. Which one do you prefer?
Oh, people would love, I'm sure, to have the material alongside the videos. So if you wouldn't mind sending that, that would be amazing.
Yep. And also to those of you who asked a question, I cannot reply here. Feel free to drop me an email. I can reply by email.
Thank you so much. This was amazing.
My pleasure.
Yes, thank you. I hope everyone has a good rest of their week and a happy holidays.
Okay, thank you.
Thanks.